Welcome. Today's colloquium speaker is Alina Donea. So she graduated in physics from Bucharest University, and interestingly, she started there a PhD. Well, after she graduated, she went to Germany for a PhD, but did theoretical modelling of relativistic jets and accretion. But before she finished her PhD, she met Charlie Lindsay and decided that she should change gears to move to seismic sources of solar quakes. But I guess he didn't make a big enough impression because she still did a postdoctoral research in black holes. But then when power solar quakes were detected in 2003, that was what finally convinced her to move totally into the field of solar physics. And then since 2004, she's been working on helioseismology and related subjects at Monash University in Melbourne. And today she'll talk about analysis of acoustic emission from quiet sun areas. And I should just give a warning that if I jump up in the middle of your talk, it's not anything to do with you, it's probably because Croatia have scored.
How much time do I have? Because I know. Would you give me a warning, or can we stay here as long as?
I mean, when people start leaving, then probably time to stop.
Yeah, good. Thank you for having an interest in this topic, because that's why I suppose you are here to listen something about the quiet sun. I want to say that the quiet sun isn't as boring as I thought initially when I wanted to do something interesting in quiet sun, in solar physics. I wanted to look at solar flares and solar quakes with Charlie, and that's how I started doing helioseismology. Of course, looking at big impacts, big seismic signatures, compare them against the quiet sun. I never had, really an interest in quiet sun till, again, Charlie pointed to me that the statistics that we have with the quiet sun is pretty interesting, and it can tell us some very good stories. So now, after a while, I've learned about all these acoustic emissions that happens in quiet sun areas, and maybe I should, I want to talk today about this. My plan is to, probably in the first half, maybe a bit less of my talk, to summarize a bit what we know about these quiet sun areas, mainly the ones surrounding active regions, and then go into something that we've done mostly recently and how this is going to take us to the future work. Now, this is our group back in Melbourne, all our PhD students. That's Paul Kelly, some of you may know it. We have one postdoc and the rest are PhD students. That's me. So we celebrated actually Paul Kelly's birthday just a month ago. I'm not going to say his age for that. So what I intend to do is this one. So discuss a bit of observational facts about acoustic oscillations and what means acoustic emission as noise. Emphasize what's interesting about the quiet sun and what are interesting locations where we can look for the quiet sun analysis. Mention a bit about these halos around active regions. It's work that we've done before. Bring in the importance of the magnetic field when we try to explain the quiet sun emission and statistics. I dare to say that in the last couple of years, I moved a bit up into the chromospheric emission, trying to understand what happens. And this came across because I started working with Phil Judge on more interesting things about chromosphere and the connection between photosphere and chromosphere. So I'm not claiming I understand the chromospheric quiet sun, but I'll try to say a few interesting things about this. So the aim is to ask myself, where do I go from here with all the statistics, with the HMI and the observations? What's the plan? And of course, in my mind, I have the dickest observations coming with the best resolution. And actually, I'm a bit scared about the resolution of dickest and what it can reveal to us. And it may really wipe out completely my understanding about the quiet sun emission as I see it through the HMI eyes. So that's a typical acoustic halo. It shows amplitudes of the local solar oscillations. Now, I'm going to probably wave a bit more the hands. It's good physical exercise, but I'm really looking at oscillations in the sun at different local points. in the areas of interest, and I'm calling this local oscillations. So when I'm studying the local oscillation of different frequencies, that I'm really looking at the power in these oscillations at these particular areas. And we can see, so this is the signature of an active region, so that means high magnetic field. And I can identify these acoustic halos at frequencies above the cutoff frequencies. It's typical, you know, many people have discovered this. I just want to say that I believe that Doug and Charlie pointed this for the first time in '92, if I'm not wrong, but long time ago, but it's still good. Doug is here and he can tell me the first feelings about discovering, you know, acoustic halos here. But what's interesting here that as we go to higher and higher frequencies, we don't really see this local enhancement of the oscillations and its power. This is just standard technique doing Fourier analysis and identifying halos. I want to emphasize that as we go to higher altitudes into upper photosphere and chromosphere, and I'm looking at, let me see, AIA 1700 and AIA 1600, we discovered halos of the local perturbation, again, halo enhanced oscillations at even these heights. So this is a result published by Paul Rajaguru, who is also in helioseismology. And he has here, I've just copied here his comments about these spatial patterns that he noticed in here. Of course, I think I should write that many people are interested in acoustic halos, in local emissions, and the connection to the magnetic field structures, and finding interrelations between what is emitted at the photospheric level, at chromospheric level, and high. So overall,
a quick question.
Yes.
Those that are darker, that's just a suppression.
Yeah, that's suppression. So that's
it's still a halo, but it's.
So what we see as halos is surrounding the magnetic field strong areas. So it's the quiet sun that neighbors that strong magnetic field.
Yeah, but you call a halo both things, whether there's an amplification or a suppression.
I would call it's the amplification, it's the enhancement in the local emission that we see around active regions.
So there's
the
two
magnetic
on the left and not.
This one, it's the contra. I don't know that. I can see it on my screen. There is a bit of the enhancement in here, not as strong as we see it here at 8 millihertz. Okay. So the idea behind this representation is to show that we should go to even higher frequencies to look for halos as we search these at different wavelengths. Yeah, so halos surround strong magnetic field areas. So these are, again, acoustic local halos oscillations. Now, we did with holography, when I worked with Charlie, and we looked at emission. So normally in the sun, we will have these local oscillations at a given pixel, a given area. But we will also have some local sources being generated extra. So we call this emission. So my hands, in terms of simulating this, will show me this local emission that we see in halos. But we'll have some, sudden sources that are part of, generating the noise inside the sun. So I'm having the sources coming and going inside the sun, and some local response of the photosphere that we observe. I don't know how I can oscillate. So, but this is what happens in what we observe here. This is a map of the acoustic emission. So I'm really looking at tiny sources that may generate acoustic noise appearing on this particular active region. And I can see that the density of the emission, the intensity of the emission is again higher, stronger around the strong magnetic area of these active regions. The active region is pretty large, and this is its quiet sun, And inside, so in the neighboring of the active region, in the quiet sun, we see this enhancement of the acoustic emission. So we don't look anymore at how the surface oscillates like this, because that's given by the halos in the previous slide. I'm looking now at all these small sources that pop up and come in and around the active region. We still don't know what's the origin of these sources, and we have many theories, starting with waves, acoustic waves going up, magnetoacoustically change into fast waves, refracting back into the quiet sun after they reach C equals A layer, which means the alpha wave speed equals the sound speed at that position. So we can have refraction, it may be acoustic jackets, it could be anything. So I'm not interested in today. I wouldn't like to focus more on the source of the mechanism of these sources. So if I'm hoping you understand the difference between the local emission and all these tiny sources that can pop up at any time around active regions. So this is what we see here, acoustic emission. So what's interesting here is that we see glories. We call glories really very, tiny sources that we call also events, conspicuous events that appear in these glories, in the halos. We also see a general halo that's spotted in yellow here with contour plots, but we also discover something interesting, what's called a plateau, just around the active region here, where the emission starts increasing to 50% when you compare it with the quiet sun. So this is stuff that we publish. We claim that we understand the morphology of acoustic halos, acoustic emission in the quiet sun surrounding active regions. And we can bring in as many active regions as we want for doing this analysis. Now, here I'm putting together these two kinds of acoustic analysis. The emission power, which represents the emission of these sources at different frequencies, and you see that the dominance comes in at 6 millihertz. It's normalized to the quiet sun, and here I'm having the local power, so the power locally emitted into the halos. There is a spatial correlation, but as you see from images, or we can bring in more statistics, but we look at two different phenomena, right? The sourcing here and the response of the local environment. Allow me to skip a few of these. Now, zoom in version of into the quiet sun, again, surrounding active regions, tell us this story. So we have, again, a local acoustic power, at 6 millihertz. The black contours here is the seismic source. So again, we have responses of the photosphere, as you see it in the first image, and then tiny sources popping up at different locations are shown by the black contours here. Now we have here the vertical magnetic field to emphasize that these glories appear where the magnetic field is really very quiet. So a lack of magnetic field allows for seismic sources to develop, to emanate. Now this is inclination, so we bring in vector magnetograms as well when we discuss the magnetic field structure of these halos. Now this is an AIA 1700 emission to show that if I look from the chromospheric point of view, this is upper photosphere, I'm still seeing a correlation here between what means a quiet chromospheric area and the emission.
What's the size of the pixel?
The pixels here, the HMI pixel, I think it's 0. Yeah. Now, the seismic sources that we identify, actually this cross here shows me what's the size of a seismic source, as the holography can offer us in terms of, size is 2.5 megameters. There was a question.
Yeah, so how do you determine that it's a source?
So in holography, we collect the acoustic signal inside an area of interest. We call it pupil. And then we reflect back in time into what's called a focal point through a model of the sun, the signal, to identify a possible source at the center of this pupil. And then this pupil is really collecting information across the image. And that's how we identify sources in holography, providing that we know what's the model of the sun through which the acoustic waves propagate back in time. So with other words, if there is a source generating some acoustic noise here, then we know how the acoustic waves travel through the sun and reflect and come up all over the place. Now we just have this pupil that collects the local information, travels back in time into the origin. And if there is something really interesting being emitted from the source, then it's easy to recollect it and put it back inside. If there is no source, then of course the signal collected in the pupil would be very small. So that's how we, I think. Yes?
What is your definition of quiet sun? It seems that some of these cover the area where you expect the factor to be. But you're talking about quiet sun surrounding the active
That's the thing, yes. So we pretend this is not exactly a pure quiet sun because we are still under the influence of an active region. We are still under the magnetic canopy that, the chromosphere has this magnetic structure. So we are still sitting under the magnetic canopy of the active region. So it's what we thought was quiet sun, and this actually now is changing a bit because we moved, and this is my second part of my talk, we moved far away from active regions to understand exactly what means a quiet sun.
So these halos do overlap with the facula that you see in white light?
They do, right? Yeah. All right, this is just to show that we had fun scanning and looking at different statistic properties of acoustic halos and emissions, showing that that's inside the sunspot where the magnetic field is very strong. And as you move away from the magnetic field, you can see the halo increasing. This is radius, this is intensity or power, and then it's decreasing. And probably the real quiet sun would start once the halo has finished and, it go up. But this is a different kind of emission here. Now, that's just to have fun looking at, so the halo, claiming it's more like a disk, we really open the disk and look at different structures to identify features into this. So we have acoustic power, and then that's the magnetic field configurations. But it's really hard, to visualize this. We really need some machine learning objects to find features in images like this. So we prefer to go into statistics.
Before we get off the topic of sources, how high in the atmosphere are the sources that you're talking about?
We observe at the height of, what's the height of the HMI observation? Is it 150 kilometers above the photosphere? I don't know, what's the observation. So we use the HMI observations. Is it, I think it's 150 kilometers.
We really can't resolve the height to within better than, say, 500 or 1,000 kilometers acoustically.
Is source necessarily the correct word? I mean, you could have a scattering site that the regression map would pick up some. If you had
let's call it emission then, or radiative local.
Okay.
We still see emission, radiative emission. Acoustic waves being radiated from that particular point at the resolution.
If you have a generalized wave field and you have a lot of scattering sites, those sites would look like sources, even though they're not physically acoustic sources.
Yeah.
Right.
All right. I'll skip that one and this one. Now, I'm trying not to move away from active regions, but not before just emphasizing that when you have two active regions together, the acoustic halos and even the emission in between them is actually a collaborative effect of these two active regions, and you get even a more enhanced emission in between what's called a bridge, acoustic bridge. That's something that we haven't really studied completely, but it's still an interesting thing to look at. What happens when in the so-called quiet sun area between two active regions or even two sunspots that get together. It's an interesting aspect to look at. All right, so I'm going to just say a few conclusions about active regions and the quiet sun. We have now, I believe, a great diagnostic, improved seismic diagnostics for the quiet sun. Regions of suppression, as we identified, are surrounded by halos of enhanced local seismic power. We also have seismic emission. Then the seismic power halos, they contract and weaken with increasing frequency. So we can again look at the morphology, dependence on frequencies, dependence on the magnetic field. The seismic emission halo, or these glories, mini sources that we see, weakens also with increasing frequency. Seismic emission can go as high as 240% of the quiet sun power in the very compact kernels. That's a lot, and we want to know why. And I'm really looking forward to have Dickist looking into, zooming into one of these areas to tell us more about the local conditions. And of course, the penumbra is telling, the edge of the penumbra is actually telling us where to start looking for halos and where to finish understanding the properties of halos. Now, let's move out. Let's move to, as far away as we can from large active regions. I try to, prepare myself on understanding what means Dickist in terms of the resolution and what's going to offer to us. And I found the EBIS observations. Maybe everyone is familiar. I've stolen them from their webpage. Different wavelengths, starting with the photosphere. I'm looking at so many tiny structures and faculae, and I even see magnetic fibrils into that. So I think I'm ready to understand what happens to the quiet sun at this resolution when it's coming. But of course, for the moment, I'm still limited by the HMI observations. So we had two aims when we started looking at quiet sun far away from active regions. We wanted to understand the chromosphere, of course, in the quiet sun, and we also wanted to understand the local response of the photosphere. For the chromospheric part, I have a student. She's really into iris analysis, and she's the expert. I wish I can keep her forever in our group. But for the photosphere, I thought I'll just bring in my experience in studying acoustic oscillations for this. So the points here that I'm trying to follow from now on is to try to understand the quiet sun chromosphere and the quiet sun photosphere, keeping in mind some of the theoretical work that we also do in our group back in Melbourne. For example, the acoustic cutoff frequency plays an important role in establishing the wave propagation conditions and in finding regions in the solar atmosphere where the waves are strongly reflected. And then I want to keep in my mind that study of waves and oscillations in the different plasma settings are important. So now I'm looking at umbra, penumbra, a network, an inter-network relation. So I'm learning about supergranules and the physics of them and what happens to the magnetic field at the edge of the supergranule, inside supergranule. I've been learning more about plumes during my visit here now. So all these have an are important for studying the transport of energy from one place in the photosphere up into the chromosphere. Right? So Daniela, she is my PhD student, had the freedom to choose whatever she wants in the quiet sun. So we were a bit biased because she looked first at the IRIS observations to pick up what IRIS provides as a quiet sun. And then I chose these areas that IRIS covered to do my acoustic analysis. So she picked up a few areas. She called this quiet sun, which is really, I've learned that there is nothing like quiet sun. But anyway, we claim that this is one of the quietest place. But this is still a strange definition because we picked up the time when this is not the minimum of the solar cycle yet for what we defined a quiet sun, but it's still useful. So what we definitely wanted is to have a piece of a quiet sun that is as close as possible to the center of the solar disk, so that when I do the helioseismology analysis, I get all the full power line of sight velocities, and I improve so that I have improved statistics in helioseismology. So we managed to identify 3 areas of interest. So this is still a bit of quiet sun around the sunspot. That's why she named it active region quiet sun. But it's a tiny sunspot, not a massive active region as the one that you've seen before. Now, these 2 are quiet sun areas in just under a coronal hole. I mean, the magnetic field definitely has to be an open configuration because there is this huge coronal hole just above. And of course, I wouldn't explain too much about iris statistics here, but just to show you where we stay with the magnesium 2K line, these are the active regions, the zones of interest. Now, that's quiet sun. We still see supergranules, the magnetic field network is visible in this emission as well. So I would define this as being a supergranule. So that was a learning curve for me, actually, to learn about all these. So I'm hoping if I say something or you can improve my knowledge, please step in. So the slit of iris, we needed, the slit to identify velocities and all these spectral properties. So the slit is just passing through an interesting areas of supergranules network where the magnetic field is much stronger in the quiet sun, another supergranule here, another piece of network here, and then another bit of supergranule here. Oops. Okay. Now for the sunspot area, the slit, do you see the slit? Mm-hmm. No? Yeah? So the slit is really going through a bit of what we call acoustic halo, as I've described it before when I do the photospheric analysis, but it also reaches this quietish area where I'm having another supergranule here and a bit of network in here. So we really focused on those specific areas to understand then the link between photosphere and the BAF chromosphere given by these observations. So in magnetic field, we could see mixed polarities. The magnetic field is evolving, flux emergencies. It's so overwhelming to look at 24 hours of magnetic evolution for these particular areas. Now, the quiet sun in the under a coronal hole, it's this one, and that's the second coronal hole in here. And Dana is going to submit her PhD thesis this Friday, which means Thursday for me here. So I have to read it one more time before she clicks the button. So Friday before 5 p.m., everything should be click submit. All right. Now this is again the quiet sun, a different wavelength. This is probably everyone does this exercise when you start analyzing an active region, a zone of interest. Then you bring in all observations and try to get the big picture of things. Now this is AIA 304. This is AIA 1700. I'm really, this. So the slit passes through that tiny area. I think I can do that better. Through this tiny area of a network, so the magnetic field is enhanced at that location, and it's interesting to look at. Now, I see this supergranule here that it's really solidly does exist for as much as 24 hours of observation, which is pretty cool. I didn't know that they last that long. Now that's the acoustic power analysis, but I have to actually come back to this one to show you the big view because it's very noisy. There is quiet sun has noise in it, right? This is all we can get from this sourcing. Okay, Dana did a bit more work on looking at separately at whatever she could really squeeze from the iris analysis in terms of what the observation from that slit provides. So this is the active the quiet sun in the neighboring of that sunspot. And we have here, I wish I can read that. Let me just say here. So this is the magnetic 2, the K2 peak, and this is the magnesium 2 line, and that's, where is it? That's the peak position in the line of magnesium 2K line, and this is the minima in the position. So that's evolution in time of that particular line in the iris. Personally, I know that she's very thorough with the analysis. I was more interested in the time series and what I learned from this, especially when the slit crosses one of these supergranule. Now, what I'm visually learning from this is that when the slit is, when this emission magnesium line, K line, crosses some magnetic field configurations, highly enhanced magnetic field in the quiet sun, then you see how the emission, the radiation is suppressed. In the quiet sun area, so this is the supergranule here, I do see the local oscillations. So these are the 5-minute oscillations that reach up into the chromosphere. So that's good. So that makes me to find now an analogy between the photosphere and the chromosphere above in terms of what oscillates and what is suppressed. Now, she also analyzed the Doppler shift from the magnesium line. And again, in the supergranule here, the Doppler shifts are pretty much normal. Let's say it's as expected, nothing exciting. But the fact that everything is under normal condition in the quiet sun chromosphere tells me that I should have the same conditions in the photosphere. You know, normal conditions, no magnetic stuff. The magnetic existence is actually doing this changes in the Doppler shift here, because I think it crosses, the slit just crosses one of the pieces of network here. All right, so that's the quiet sun, very close to a tiny spot. This is the quiet sun behavior in the chromosphere under the magnesium K line for the very quiet sun that we could find. And again, just to spot this knot here, where the magnetic clustering is so strong, allows for this chaotic motion behavior in the magnesium K line. But the quiet sun above the granule is somewhere here. I'm seeing clear oscillations reaching the chromosphere in this line. So she brought in lots of these things, statistics. I'm hoping she may give a talk because she's coming here in 2 weeks' time. Now, bringing in the statistics of what she analyzed here, we did this plot where we look at the Gaussian fits of the integrated intensity distribution. So she measured the intensity distribution for different spots of this area of quiet sun. So she picked up, for example, the area. This is the net. So this is the intensity distribution in the network. So the magnetic field is strong in the networks. And she looked. IRIS provided this details. Now she looked at the intensity distribution inside the supergranule, and she came up with this histogram. So I can see here 3 different regimes in terms of how the chromosphere responds to the local environment, to where there is more magnetic field or less magnetic field, penetrating and going up from the photosphere. This is a very intensive zone where the magnetic field is stronger, still under the limits of the quiet sun. So we need to understand why this happens, and that's why we need to bring in more specialists in chromosphere to explain, to help us understand why we have different regimes and why the magnesium K line responds. Yeah.
Is the 30, 60, and 280, 310 Gauss, or what unit is that?
This one.
Yeah.
Oh, yes. So that's active region. I'll go back to this one. So she mentioned. So she picked up a specific length of the slit. So she picked up those pixels within that. Let's say if the slit goes through this magnetic area, a strong magnetic area, then that's how she defined the network. Now this area from, let's say, this position to this position. So the slit length covers the quiet Yeah, it's the position of the slit, really.
So it's just like
Right.
segments. I guess.
Yeah. But behind, so the position is biased by the fact that there is magnetic field, a given intensity into that. All right, so after this, I told my student, okay, you keep looking at the statistics, I'll start doing my own helioseismologist analysis. So when you unleash PhD students into Python codes, they come up with crazy correlations like this. So she really correlated and tried to do correlations, everything on the, whatever IRIS provides here with a very fancy, sophisticated Python code. I'm not going to decipher this because I just wanted to say that they can do a lot if you just let them do so. There is a connection here. Now, what you would see here is the intensity of the emission line, width of the emission line, Doppler, magnetic field. She really brought in whatever IRIS could provide her for 3 different areas in the quiet sun: internetwork, network, and enhanced network where the magnetic field is strong. So, but I will probably need to talk about just 1 hour for the particular this. All right, so let's assume that we kind of know what's the chromospheric response above the quiet sun, what is this emission, this line, magnesium K line, telling us. We looked also at flares in magnesium K line to compare quiet sun versus activity. Now, I wanted to bring in the AIA 1700 observations for these quiet sun areas versus the HMI Dopplerograms. So this is, we've been looking with Charlie at these in the last days. What do I see here? I'm seeing the AIA 1600 time series. This is time, this is velocity. Oh gosh, okay. I'm seeing lots of oscillations. I can recognize the 5-minute oscillation in this time, just plain time series here. I can see a bit of, do you see there is a temporal correlation with the Doppler motion? So again, we're shifting hands, they maybe do that. This is the velocity oscillation, local oscillation in the sun, and this is the AIA 1600. So there is a spatial correlation, a temporal correlation into that, if I want to move to these wavelengths. Now, bringing in the 1600, I can see again that there is very good correlation here. So now probably I can, start layering up all the observations and try out to, bring in more physics on what happens in the quiet sun. Now, so I'm claiming I've done the acoustic analysis of the quiet sun, and this is what we came up with. So I'm looking at the very quiet sun area and in the acoustic emission. So that's the local power at 3 millihertz, and this is the local power at 6 millihertz in that quiet sun. So I'm really looking at how much power is in the local oscillation. But I also try to identify sources, seismic sources inside these areas, right, by applying holography to the data. So that's the seismic source map at 3 millihertz, and this is at 6 millihertz. So what am I seeing? The areas where there is a bit of magnetic field in the network absorbs, suppresses the local oscillations. And I don't have also not that much sources generating at 3 millihertz or 6 millihertz. But I have some areas where, especially in the supergranules, it's very hard to see it on this plot, but maybe, see that bright area here? This is a supergranule. So at 6 millihertz, I was never looking that, with such a zoom in intensity at this. So a supergranule in its middle part has emission at 6 millihertz. I'll come back to this. All right, this is the local acoustic power, and I'm seeing something else. That's a different story. Around the magnetic field areas in the network, I'm seeing acoustic power halos, similar to what I did see for the big active regions. So the local oscillations are enhanced around the magnetic areas here. But sources, so you know those tiny sources generated at 6 millihertz, appear to just be a bit enhanced in the middle of the supergranules. Not on the edge of supergranule, because the magnetic field is still there, suppressing everything. And that makes sense because this plot here is actually showing me the same behavior of the acoustic, of the local acoustic power at different magnetic fields and different frequencies. So at 6 millihertz, I'm seeing an enhancement of the acoustic power for intermediate magnetic fields as I see them in the quiet zone, in the network. So the network, in average, will have a magnetic field of, what, about 100 Gauss, 150, probably not more than this. So I will be within this regime. So I'm starting seeing acoustic halos around tiny areas magnetic network at 6 millihertz and above a bit. I do see them. That is new for us because, and I move to the next plot here. That is new because why do we have enhanced seismic emission, you know, those tiny sources, popping up in the middle of a granule somewhere? Now, this is just to show you the correlation, again, between the acoustic power around the magnetic areas in the quiet sun. You can recognize the supergranules and a bit of features inside of supergranules here. We plotted for the magnetic field the local square magnetic information. So we still have tiny local acoustic enhancement around these areas. Nothing in this area because the magnetic field is pretty weak. So the quiet sun is not quiet at all, right? So it's very important for me at this step to understand more about the magnetic field that exists locally in the network. So that's a new research field for me to understand this. And I've been reading papers and they have different opinions and it's very challenging, right? Now I'm putting now the emission. So what I'm comparing now is the local power, shaking my hands, the local power versus the emission, you know, possible sources that emit at 6 millihertz. And what do I see? Acoustic source power is pretty, you know, boring. There is nothing, maybe a part of one of these supergranules that a bit emits. So I'm not seeing anything like the beautiful acoustic emission halos surrounding active regions. And that's interesting because now I'm having enhanced acoustic power, but no sources coming in here. I mean, they are there, but it's nothing conspicuous here. So acoustic noise sources are most prolific in supergranule interiors, where the magnetic field is around 10 Gauss or less. Right? So this, we mean there are sources, mini sources. Well, acoustic noise, this is really we're talking about noise. I mean, when I say sources, I'm thinking at noise in the sun. And we know that the sun is pretty noisy, right? So we keep looking for the same thing in the other active regions, and we identify also a bit of acoustic power halos in here let me see what we have here. Local acoustic power at 3 millihertz, at 6 millihertz, and the emission coming from the sources. Now the slit was just crossing this, and now I can make an analogy between what happens with the oscillations in the photosphere and in the chromosphere. We look then at the quiet sun under the coronal hole, and again here we identify some patches, very hard to see on this plot, some patches of emission that overlaps with the supergranules, with the top of the supergranules. So that's observational fact. We need now to go back into the theoretical part and understand why we have this enhanced emission here. Now you can see the acoustic halo around some magnetic areas. These are not sunspots, it's just some magnetic plages in this quiet sun area under a coronal hole. Of course, we can bring in more statistics about what happens with the number of pixels having this enhanced local acoustic power at 6 millihertz. I even went up to 8 millihertz to understand what happens with the acoustics here. Now, I found an interesting software where you can pick up a mask of a different color and then instantaneously look at the distribution of the pixels in this. So what I can say is that where we have enhanced acoustic local power at 6 millihertz, then definitely that tells me that those areas, those pixels emitting locally power will shift to that high power that we expect. Now the background here in the distribution is like the whole statistics over the area. So I'm more interested in small patches around magnetic fields. Now the iris slit just cross at this location, so that's an interesting area for me to study, and this is just statistically showing me that distribution. Then scatter plots, which I don't really like, but everyone seems to do this. When you have large statistics, you have this. So what I plotted here is, again, sources, emission in sources versus the local oscillation at 3 millihertz and at 6 millihertz. There is a correlation. I can see it in this distribution. Different colors represent different masks that we choose. Right, so what's the correlation here? I'm thinking, again, waving my hand. So this is the local emission, and this is the source. Maybe this source that acts at one stage, so the noise generated is actually locally influencing the response of the photosphere at the existence of this source. All right. So I've discussed about this. I just put it back here. Now, two more things we wanted to do is to correlate the local acoustic power with what we call ingression. We looked at how the acoustic waves travel into the area of interest, and this is called ingression. So we wanted to now compare the local response with how much power is into the waves that come into that area. So we looked at the ingression control correlation of this phenomenon, so local versus stuff going in. And interestingly, we found that, the second plot, this one, it's pretty uniform, right? So that tells me that there is a strong correlation when we look at the values, but it's nothing peculiar here, nothing interesting. So that tells me that the magnetic field doesn't have a say into what happens when the acoustic waves go inside and influence the local activity here. So we call this insensitive to the magnetic field response. So the Doppler sensitivity of the solar photosphere to incoming acoustic waves is about the same in acoustic power halos, those enhancements, as in the quiet sun. Something to learn about that. So this is all about local oscillations versus stuff going in. Then we did another experiment. We said, let's look at the local response versus when we have a source emitting acoustic waves all over the place. Because that tells me, again, something about the dynamic of generating noise at that location. And we can see a correlation here. You can see acoustic power, local oscillations, and a high correlation, control correlation at 6 millihertz. And then, that's my last graph. What do we have here? The local acoustic power versus, did I show you that before? Yeah, local acoustic power again versus the seismic sources here. I'm interested now in looking at whatever means magnetic field at 10 Gauss or less. But I'm in a big trouble because when I talk to KD about the magnetic structure of quiet sun, she tells me that HMI doesn't have the right, with 10 Gauss, I'm within the errors of the magnetograms. So definitely I have to wait now to zooming into understanding what's the magnetic field in the in the middle of the granules to come up with a better understanding of why this happens in supergranules and at the edges. So the conclusion is that I believe we have greatly improved the seismic diagnostic of the quiet sun. Now I understand better what means quiet sun. I'm dreading to look at more pixels. I need to change my glasses, but it's the statistics that has to come in from now on to understand what happens here. Now, I've learned that the region of suppression are surrounded by halos of enhanced local seismic amplitude, as well as enhanced seismic emission from time to time. I've learned also that supergranules are interesting, and I need the KIST from now on to come up with something. Yes, thank you.
Questions? Kevin?
So around in the chromosphere, in calcium 8542 or H alpha, we see a strong suppression of halos around network active region suppression at 6 millihertz.
Okay.
Right, due to the canopy, the magnetic field, or it's correlated with the presence of the fibrils, so we're indicating the sort of horizontal field there. Is it possible that there's, they're reflecting, there's some process that's, reflecting those waves down, and that's producing the enhancement then down in the photosphere? Is there something? Because we don't know where those waves go, where they reach the chromosphere.
Then we have to look at, so this reflection, so I'm having here two images. So we have some waves coming from above, reaching down into the photosphere and enhancing this local emission or sourcing it. But then we have also another possibility where acoustic waves travel up and then get reflected somewhere in the magnetic canopy, or ideally is where we understand that the alpha velocity equals the sound speed. That's where the conversion happens in a very efficient way so that some energy goes back. So now the question is to identify where is this layer, and if we think at a reflection of this way, if we think at just waves coming up from above, then that's still hard to understand because the chromosphere is pretty dense and the gradient of pressure and temperature is pretty high. So I don't have an answer for this, especially for the quiet sun.
I'm just struck by how similar those halo enhancements you see in the photosphere
it's actually
would be to the suppression you would see in the
chromosphere. The halos are more expanded than the one in the photosphere because that reflects how the magnetic field is actually opening up. And that's an analogy that we understand.
So you've got suppression of the power where the magnetic field is strong.
Yes.
And you've got excess power surrounding that. If you average over an entire region, is there more power, acoustic power coming out, or is it the same as you get far away from a magnetic region?
If I average over a quiet sun area.
If you average over one of these suppression areas plus the blurry surrounding
I would say,
and take the power per unit area.
Yeah, I would probably easily miss what we see now into this because everything is so average. I can answer it with another experiment that we did when we looked at the acoustic halos around active regions, and we wanted to normalize that emission with respect to the quiet sun. What we did was we just picked a mask in the quiet sun, average over it, and everything was normalized to that value. We never looked inside, so the mask was just picking up whatever was in the quiet sun. It could have been 2, 3 supergranules, a few of these networks. So now it's different. We zoom in. We looked at the structure in the quiet sun. So I would say that, these enhancements are not huge, like 100% above the quiet sun. This is maybe 2, 3 times. So the enhancement is 2 or 3 times larger than the quiet sun.
But the enhancement plus the suppression region, there's more power coming out in this some region.
Yes, there is more power than the quiet. I mean, now we have to define what's quiet sun really, because this is still part of the quiet sun. Yeah, there is a bit of local enhancement because of the magnetic field existence. So we talk about local enhancement, the local oscillations, I think.
Yeah.
Okay, so you talk about enhanced power in the oscillations, and you talk about emission, enhanced emission. So how much of the enhanced power can you account for in terms of enhanced emission?
Well, emission.
That's a sensible question.
So emission is when we identify sources.
Yeah.
Noise, localized source. I can, identify. It's there. It emits.
Right.
Now, how quantitatively I can define the source by giving it some information about the power that has in emission. Right? Power is the property of the source itself.
Well, I guess what I'm asking is there some enhancement in the power of the oscillations just due to the structure of the atmosphere, or is it because it's being forced somehow?
So we have, so if it's a local oscillation, this is enhanced. That's one thing. But if I'm having a big source appearing at one stage, that's another thing. Hopefully, I don't know.
Right, but you figured that if you have more sources, you have more power. Right?
Yes,
but
of course.
Can you account for the extra power in terms of sources? Or do you...
Probably need to look more into this to be more quantitative in answering that question. So far, we're still very visual in understanding where things happen and compare them to an average noise level. Right? So we haven't yet started explaining these things in terms of the mechanism of sourcing here, or why is that? This is just observational results that we have.
So to look for sources, you were using HMI data, which is full disk data.
Yes.
Can you look for similar sources over a very small field of view?
So we need to identify these sources. We need to collect enough signal into our area of integration to come up with a visible source. Because if we don't collect enough signal back into, let's say, where is the source, we don't see anything. The more signal, it's like integrating over up to 24 hours of observation to collect the information of this oscillation.
24 hours of observation
Yeah,
with Dickies is going to be difficult.
Well, I know, but I've learned that 1 hour of observation with Dickies will give me more than 40 gigabytes of a tiny data cube. And I need to start now ordering the biggest computer that Australia can have to allow to analyze a small area on the sun. So yeah, the statistics is going to be completely different.
To follow up on that, is the DKIST field of view big enough to put a pupil that will allow you to measure the local?
The answer is no, we can't. Yeah. So we need to look only at local enhanced power. And for holography, we still rely on HMI, right, Doug? Because we need a big, yes. And I'm learning now with Phil on what would be the biggest field of view that we can collect.
Yeah, you don't need high resolution to do the holography. It doesn't,
exactly.
It doesn't gain you anything.
So
but the local emission, the local is what you will learn.
Yeah, we will look
about,
at the. So from what I've done an experiment. Remember, Phil, what we did when we look at the best field of view that Dickies can pick up for us, and it should be, if I remember, I don't remember numbers yet, but will be more or less of this area, right? The largest field of view that we can collect for local power. Of course, we can choose even a tiny area and look at the local oscillations with the best resolution. But holography is not, we can't apply to the thickest. But they will be complementary, where with the holography, if we identify some area of enhanced seismic emission, then quickly we can go into the KIST and identify the local properties.
Kevin again?
So those sources, I understand that they're identified from 24 hours or some extended time series. So those sources aren't necessarily individual events happening. They're a 24-hour average of the source. And within the background of an evolving application, so what they are physically.
You want to?
I just wanted to add that in the context of what Mark's comment was about whether you have a source or a scatterer, and also in the context of what Kevin was talking about with the chromosphere. I mean, this is I think most of your comments were in the context of what I would consider to be linear wave theory. And but that's not what you've got in the chromosphere. So what I'm trying to say is that I think many of the results might be interpreted in a rather simple way, namely the steepening of the waves in a nonlinear fashion as they propagate upwards through the pressure gradient, the density gradient. And then you have, then that leads to natural sources in the chromosphere, because, you know, you only have a source by projection onto a linear system. If you've got a nonlinear system, then you end up with higher frequencies as a result of steepening and all this stuff. So I think I'm having difficulty in wrapping my head around what linear theory means when you step into such a nonlinear regime. And so I think that, you know, some of the results you presented are rather interesting. I'm not sure what physics what they mean yet, but I'm sure that pursuing it will lead something of interest. But I think you do need to keep in mind that, you know, you've got an implicit source of the nonlinearity of waves from the chromospheric density gradient, almost without reference to the magnetic field even. So for instance, slow modes are a perfectly natural way in which these things propagate. That's essentially the sound speed. Whether you've got a magnetic field there or not, you're still going to get this generation of shocks. I mean, make it converted into another magnetosonic mode, and you might not see as much power. But those kind of things, I think it's very, very interesting to probe what those things might mean.
Curiously, though, around in these canopies is exactly where we don't see the shocks in the chromosphere.
Yeah,
the way
that's a
the
result.
shocks aren't there.
Right. So that's the result that we found with, actually when I was working in Monash in 1999, so it's a paper by Judge Tarbell and Wilhelm that talks about a lot of the stuff you talked about, but with SOHO, in which we looked at SUMA data along with MDI. Of course, we have a different set of data here, but yeah, I mean, I think it's pretty consistent. The data that are published are not as inconsistent as one might think. Yeah. And as to reflections and stuff off canopies, I don't know, depends. You don't see much in the way of an oscillation by the time you get to the β=1 surface. Then that's kind of a non-starter, I think. So I don't know what the dynamics is about, but it's very, very interesting.
Well, I'm not the expert in chromosphere here. It's just that I want to show how we step into this research to try to make our minds about what means emission in the photosphere, and if there is a link, be it from above, down, or from beneath the photosphere going up, in terms of wave propagation. And yeah, we're still learning.